I think both of you got to hear the announcements ad nauseum, so hopefully you're okay with those. Any questions on anything we've done so far while the projector is trying to turn on? Some of the projectors in some class you turn them on and they're on. This one takes its time. Okay. Others of them seem to turn off quickly. This one does too. Okay. All right. No questions? We're in Chapter 2, First Order Differential Equations, and Section 2.3, Linear Equations. All right. I hope you remember what the deal was and how we proceeded with linear equations. My memory is we're on example 4. Now, just before example 4, we talked about singular points, okay? And those are points where are potentially troublesome points where things may not go as you want them to go, okay? So let's take a look at example 4, which I bet you will have some. Find the general solution of, let me get my pen set up, x squared minus 9 dy dx plus xy is equal to 0. Okay. All right. Think you can separate those? Actually, yes, you can, can't you? Okay. But let's not. I think they want us to do it linear. We'll come back and do it separation if you want to. Wow. Okay. Wow. I really, there's a part of me that sees absolutely no reason to do linear if you can separate. But let's go and do it. Just for the practice of linear. Okay. Is it a linear equation? It is separable. Is it linear? All that makes it linear, look at the y's and derivatives of y's. All your y's and derivatives of y, if they are all linear, it's linear in y. dy dx, that's not squared. There's no y times dy dx, that's linear. Y, it's not squared. It's not 1 over y. It's not got a dy times it or anything else, so it's linear. Yeah, that's linear in y. So the next question is it in standard form? Why not?
Because that
x squared minus 9 is the coefficient of dy dx. We don't want that. We want that coefficient to be 1. So what can we do? Divide both sides, in fact, everything on every side by x squared minus 9. I'm just doing that just to be complete about it. That goes to 0, and then we have dy dx all by itself now, plus x over x squared minus 9 times y is equal to 0. Is that in standard form? Yes, it is. What's the first step then?
make the x squared minus 9 p of x.
Okay. Make it p of x. You're absolutely right. Let that be p of x. And then what do you do with that p of x?
Take the
Integral. So we're doing the integral of x over x squared minus 9 dx. Okay? How do you do that integral?
trig substitution.
Looks like what?
Trig substitution.
Perhaps you could if you really want to work hard, but I'm way too lazy for that.
But you want to take the exponential that e to an integral.
Okay, say that one more time.
You want to exponentiate that as the p of x,
Okay.
e to the integral.
Okay, yeah, you're going to do that in a minute, but let's integrate it first. How do we integrate it?
Parts.
Second? Okay,
The fraction thing.
Okay, you could certainly do it partial fractions. Again, if you want to work sort of hard. I'm a little lazier than that.
And you're lazy.
Yeah, awfully lazy. How about what's one of the first, where did you go? There we go. I wasn't even touching it. Okay. One of the first things you did in integration after you did the simple stuff, say again? Use substitution. Would that work? What would you let u be? X. You choose to use substitution be the most complicated part.
X squared minus.
Innermost part, yeah, x squared minus 9. X squared minus 9. Then du is equal to, say again? 2x dx. Yes. Well, we really don't have an 2x dx. We have an x dx, so let's divide both sides by 2. Okay. And now I think we can go to town with it. That would now be integral of, it would be 1/2 the integral of du over u. Right? You change to the u's and du's. So your du over 2 is x dx. There's your x dx. You put the 1 over 2 out front, and the bottom is just a u. And what is that? Say again? Natural log of u. Okay? Now, because Bill's already looked ahead and knows what he's going to do next, I want to change that form ever so slightly. What's the next thing you're going to do? Bill, you said it?
Oh, the E.
You're going to E it, aren't you? Well, I don't want the half it where it is now if I'm going to E it. I'm making up a word here. Yes. What is that going to be? The same as? I want to E only a log. I don't want to E a 1/2 a log. Log of u to the 1/2. That's it. Now when I E that, that's my integral of p of x, what's E of that? U to the 1/2. And that's it, folks. That's your integrating factor. U to the 1/2. Except, let's go back and figure out what U is, or U are. What is that? X squared minus 9 to the 1/2. Okay. That's our integrating factor. So I'm going to take that and multiply that by everything on both sides of the equation, which would then be x squared minus 9 to the 1/2 power dy dx plus, now, let's be careful with this a little bit. That's going to be, well, let's just go x squared minus 9 to the 1/2 times x squared minus 9 times y. I'll multiply the other as 0. Okay, I did that part for you, so you don't have to think about it too much. Okay, now, anytime. Now, here you have the square root of this, and here you have that. So isn't this the same as Because isn't that denominator, x squared minus 9 to the 2 halves, to the 1 power, right? And I do 1 half into 2 halves, and I get 1 half left. Okay. If I had x to the 1 half over x. Yuck! Okay. What would that be? No?
X to the 2.
Okay, this would be x to the 1 half divided by x to the 2 halves. What's the rules for dividing? Subtract the exponents and be 1 half minus 2 halves, which is negative 1 half. That's exactly what we got here.
Okay, I thought you were saying they were canceling out or something. My bad. The test.
I'm sorry?
I just gonna pick up the test.
Which test was that?
Cal 2.
Oh, I still have it up. Lucky, because usually I have it down below. Let's see, this is Cal 2. Right?
With Dawson.
Huh?
Yeah, with Dawson.
Right. Did he need his too?
Is he kicking the guys? I'm in the class with him too, so.
Yeah.
If he hasn't got his, I can take him his too.
Oh, I'm still here. I'll get there in a couple of hours. Okay. No, you don't have the key. You do?
Yeah.
You promise?
Yeah.
Okay, there's one. It may be the others that get stapled. Is that right? Let's see. No, that's a different test. There it is. Make sure there's the same test. If not, I want you to take the part. All right. Okay, so we're got it now? All right, so let's see what we got. Writing this a little bit neater. X squared minus 9 to the 1 half dy dx plus x over is it all right if I write it in, yeah, do the negative. So I think that'll be a little easier to see. X times x squared minus 9 to the minus 1 half y is equal to 0. All right. Now, what we want at this point is this to be a perfect derivative, typically of a product. In fact, what product you want it to be is y times the integrating factor. Okay? So that's what we're hoping, that this is the perfect derivative. I'm sorry that I can't write. Sorry. D by dx of y times your integrating factor, which was x squared minus 9 to the 1 half power. Okay? Let's see if it is. Well, that's the product. So that would be y dx, there that is, times this, u times dv, or d, whichever, du times v, right? Plus, that's there, y, there it is. Now, is this thing here derivative of that? That's the question. What is the derivative of this? 1 half? I see a 1 half up there. this thing to the minus 1/2. Well, got that. Times 2x. Well, that wiped out the 1/2. There's your x. Yes, it is. Perfect derivative, right? And that's equal to 0. Because that was the other side. All right. Now, if you... Can I go back and erase some stuff because I'm running out of room very rapidly here? I'm just trying to figure out what I want to erase. Let me erase all this. Is that okay? I want to leave some stuff at the beginning, and I'm going to leave it there if I can get this to erase. Because we've already used this. I'm about to wear out my screen, I think, by doing all this erasing, but hopefully not. Not until for another 1.5 years or so. Then I really don't care. I'm sorry I didn't say that. Okay. Now, what that says, if we multiply both sides by dx, okay, we have that d of y times x squared minus 9 to the 1/2 is equal to 0 dx. Okay, for whatever that's worth. That's ugly. Okay, let me clean that up some. The pen has gotten really slow. 0 dx. Okay, that's sort of dumb looking, but we got it. Okay. Now we integrate both sides, and you get y times x squared minus 9 to the 1/2. What's the antiderivative of 0? A constant. Let's call it c for now. We may change our minds later. All right. Well, what does that give us? Y is equal to, is equal to c over x squared minus 9, the square root of that. Right? One parameter system. Okay. Now, are there anything problematic about that? Okay. Well, one thing is x can't be plus or minus 3, can it? Okay. Well, looking up here, our original problem, if x was plus or minus 3, then we would have had 0 dy dx plus xy is equal to 0.
0 is equal to 0.
So that would have been problematic in the very beginning. And then when we divided by that, it made it even more problematic, okay? So it couldn't have been 3 or minus 3 really anywhere in the problem. If it were, you would have had xy is equal to 0. That means either x is 0 or y is 0, one or the other. So neither one of those are very interesting problems. But it also limits our domain, the range of which it has. Because we have it in the square root now, this has to be positive, what's in here. And for that to be positive, that means you either have to be x less than minus 3, then that would be positive, or x is greater than positive 3, because anything between minus 3 and 3 is going to be negative. That won't be allowed. So that means we're either down here or up here. And since we don't know anything more about the problem, that's all we can say. But for sure, it can't equal plus or minus 3, and it can't equal anything in between plus or minus 3. Now, there was nothing up there that stopped it from being that, so that lets you think, well, maybe in the things we did, we introduced an issue. And that's where your singular points can sometimes lead you to difficulties. So let's see what we've got. Did I do that right? Yeah, I did. Okay. So our general solution is y is equal to c over the square root of x squared minus 9. But you have to limit that to be either on minus infinity to minus 3, not including minus 3, or 3 to infinity. And without knowing any more about it, we don't know which of those we're on. If we had an initial value, yeah, we'd know, but we don't have that. So either of those will form a general solution, but nothing in between, and it can't be both at once, one or the other. Yeah, I think we've already hit the other issues there. Any questions on that? All right, did you want to do it? Separation of variables, or are you okay? Actually, if you had said yes, what we would have done was subtract that from both sides, then divide by y, and multiply by, and divide by x squared minus 9, and then write in differential form, what you'd wound up with log y is equal to the integral of that, which is basically exactly what we had here.
This wasn't bad.
No, it wasn't. So either one would have been just about the same level of complexity, okay? But they wanted you to do this, so we did it. We're very compliant, aren't we? Okay.
The easiest way is fine with me.
Okay.
Or equally easy.
Yeah. Okay. No, you wanted to do by partial fractions, okay?
Well,
I remember.
That is true.
Okay. Or by parts, or something, I don't know. Okay. Let's solve this one. Example 5. dy dx plus y is equal to x. Given that y of 0 is equal to 4. All right. This is an initial value problem. That's a really simple looking differential equation. Can we do that by separation of variables? That plus messes you all up.
I don't think so, because
No.
plus
Can't do it. So, what might you choose?
Well, we'll move that x back over. Right.
No, let's not. Say we did, okay? This is set up perfectly for linear, isn't it? Don't even have to adjust it. That's in standard form linear. dy dx is by itself. Y is only to the first power. Its coefficient is 1. And x, who cares what's on the right-hand side, is all your x. They're only x's. Last time it was 0, that was even easier. But x is okay over there. Any function of x is all right over there. Maybe hard to integrate, but it's all right, as long as it's over there. So what's your first step? Okay, first, do you see that's a linear equation? Okay.
Well, I mean, yes, because none of them are
Multiplied by
multiplied
cross terms, raised to powers,
Yeah.
fractional powers, negative powers, none of that. dy dx is the first power, y to the first power, other side is all x's. So that's linear. Okay? Is it in standard form? Why not?
Because x.
You don't like that x over there, do you? You do not at all. Okay. Standard form allows you to have any function of x over there you want to.
Oh.
Okay? Now, what makes it standard form is that the coefficient of your derivative term is 1. And it is. So that's already in standard form. What do you look for next?
You want to put that in differential form? I said, do you want to put it in differential?
No, not for linear. This isn't separable, so we don't want to do that. Later, there's going to be another form that maybe that will work in, but we're not going to do that either. We haven't gotten there yet. But once you got it in standard form for linear, what's the next thing you do? You told me last time, identify your P of x. And what's your P of x here? 1, uno. Okay? And what do we do with that? You integrate it. There it is. And what does that give you? X. Okay. And then what do you do with that? E it. Okay? So, e to the x. And now that's your integrating factor. So we're going to multiply that by every term on both sides. So we've got e to the x dy dx plus e to the x y is equal to e to the x e to the x. I'm going to write it that way. It's easier. Okay? Now, what do you want this side to be? Want it to be a perfect derivative. Okay, is it? Is this a d by dx of something? Well, the something is always going to be y times the integrating factor, e to the x. Well, let's see if it is. Well, derivative of the first times the second. Yeah, that works. Plus the second times, so this one times derivative. This one times the derivative of that. And derivative of e to the x is e to the x. So yes, it is a perfect derivative. So now we write this as a differential. Okay? And do d of y e to the x is equal to x e to the x dx. Okay? Well, derivative of perfect derivative of that, and now we integrate both sides, sorry. Forgot to say that. Integral of a perfect derivative is y e to the x, right? Ooh, what about over here? One of you said it last time. Second? By parts, that's it. What part is parts? Parts is parts. Let u equal something and dv equal something. Which is which? I'll tell you one thing, the dv is going to have the dx with it. The d's always stick together. Okay? So, which goes where? Yeah, let u equal x. Is that what you said?
Yeah, well, I said dv is dx.
Oh, no, dv is, the dx is with that, but it's e to the x dx.
That's what I meant.
I thought it was. Okay. Yeah.
What did I say?
I don't know. I couldn't understand.
I said xex, I mean, which is like
Okay. All right. Then, du is equal to dx, and v is equal to e to the x. Hey, that's working out pretty nice. So what does this integral over here become? Your u times v, which is x e to the x. Excuse me. The integral of your bottom line, which is e to the x dx. Right? That's what's on the bottom.
E to the x.
Say again? Which is e to the x. So what we have now, filling in the gap here, is y e to the x is equal to x e to the x minus e to the x. And at this point, we need a plus c, I think. Maybe not yet. Yeah, we better. Okay? Now, what do you do next? Ever can, solve for y. In other words, if you can, get an explicit form of y as a function of x, do so. So what would you do? By e to the x, e to the x, e to the x, and e to the x. That goes out, that goes out, and that goes out. So what are we left with? X minus 1 plus c. Let's write it c e to the minus x. I like that a little bit better. Is that all right? Okay. Now, but we do have an initial condition. When x is equal to 0, y is equal to 4. That means 4 is equal to 0 minus 1 plus, and what's e to the minus 0? Same as e to the 0, 1. So that's plus c. So what does that make c? C is equal to 5. So we go back to our equation here, and you have y is equal to x minus 1 plus 5e to the minus x. Okay? That may not be, oh, that's exactly the form they leave it in. Y is equal to x minus 1 plus 5e to the minus x. Okay? Now, the form right here with the c in it, here is a representation of some of that family of curves. C is 0 would be there, which would be y minus 1, right? So that's the line y is equal to x minus 1. Y-intercept of minus 1, slope of 1. Okay? That would be when c is equal to 0. Okay? When c is greater than 0, then you get the curves that are up here, including when c is equal to 5. It's that one right there. Okay? When c is less than 0, you'd have been down here, but we're not. Okay? So that's that. We say that this c e to the minus x is a transient term. That's another new term for us here. Why? Because in time, when x gets big enough, t is going to 0. Right? So then you're approaching x minus 1. So you see, after a while, no matter what c you get, it's going to be this. Y is equal to x minus 1. Or very close to that. So that last term there is transient. It is right there too. Even when it's 5. Doesn't take very far along x-axis before that's going to be such a negligible contribution. All right. Everything was going so nicely there until they've decided now to introduce a thing called a piecewise linear differential equation. So in other words, it's going to be defined one way, some values for x, and something else on another value for x. Okay? Goodness, my nose is itchy. You don't have company. It says in the construction of mathematical models, especially in biological sciences and engineering, which I think at least one of you are, right? Yeah, I thought so. I think maybe Corey too, but I can't remember. Maybe not, I don't remember. It said it can happen that one or more coefficients in a differential equation is actually a piecewise defined function. Okay? Particularly either the p of x or the f of x, that's the thing to the right of the equal sign, which Josh doesn't like. That could be a piecewise defined function. The basic idea is to solve the initial value problem in two parts, corresponding to the two intervals over which it's defined, and each part consists of a linear equation solvable by the methods that we've done in the section, and then it's possible to piece the two together so that it's a continuous function. It probably won't be smooth, but it will be continuous. It could maybe be smooth, but that's what we want. So let's do example 6. Another piecewise defined function. Okay? Okay. Where did it go? There it is. Okay. All right. All right, to erase. Okay. Example 6. dy dx plus y, ooh, that looks familiar, doesn't it? Is equal to what Josh doesn't like, f of x. Okay? We're under the condition y of 0 is equal to 0. That's even simpler than before. But in this case, f of x, you didn't like it when it was an x, you're sure not going, well, you may like it better now. F of x is equal to 1 anytime 0 is less than or equal to x is less than or equal to 1.
Did you go ahead and change x to f of x?
Second?
Did you go ahead and change the x in the initial problem to f of x?
Well, wait. Let me finish writing it, and then let me see if I can answer your question. This is true anytime x is greater than 1. Okay, now, what were you saying again?
So, like, dy dx plus y equals, it says x in the book.
It does? No, we're on example 6. Go down the page. Almost at the bottom.
Yeah, that's what I'm looking at too. Does yours say f of x?
Yeah. Example 6.
Initial value problem?
Right.
I swear.
Example 5 is that one.
Oh, look at that.
See, yours is wrong. Because you don't have an f of x.
Yeah, that's what I was thinking.
Yeah, see, that's the one we did up here. 5. That's what we only do. There. See, that's the same one, except with a different initial condition. So, you need to remember that.
Exactly. I'm going to complain. Right, that's a better business deal. Charging me $150 for it.
Yeah. Okay. That's supposed to be an f of x. Otherwise, this problem doesn't make any sense. It'd be the same problem as before, just
Well, I
a
get why you
different
didn't
initial
understand what I
value.
was asking.
Okay, so what we do, we just solve it twice. Okay? But understanding different domains, you might say here. Now, I don't see any reason yet, maybe we'll see it later, why they restricted it to always being positive, but they can do whatever they want to, I guess. Okay? And certainly 0 is included here. And that leads to a different issue with me, is why do we even mess with the second one? Because the initial value is when x is equal to 0. So who cares what's happening when x is greater than 1? I don't know. Don't have the answer to that yet, so let's proceed. All right? So let's first write down dy dx plus y is equal to f of x is 1. And this will be anytime 0 is less than or equal to x is less than or equal to 1. Okay? Now, do you like that any better than before? You still don't like having anything over there but a 0,
Like
do you?
all together.
Yeah, okay. But is this a linear equation? Is it in standard form? Yes. So how do we proceed? P of x is equal to? And what do we do with that? Integrate it. And what do you get? X. And what do you do with that? It. All right. Don't forget the it. Okay. So e to the x is your multiplying factor. Integrating factor, they call it. So now we have e to the x, dy dx, the same as we did before, plus e to the x y is equal to e to the x. Okay? Because you multiply by 1. Is that left-hand side a perfect derivative? It was before, wasn't it? It's d of e to the xy is equal to e to the x. Right? D by dx. Okay? So then move your dx over there, integrate it, and you have e to the xy is equal to e to the x plus c. Okay. Now you plug in, let's, isolate the y, and that's going to be y is equal to wait. Okay, if you like to do that, we'll do it that way. C e to the minus x. Is that what you're going to say? Okay. All right. Under the condition that y of 0 is equal to 0, so that means 0 is equal to 1 plus c. Right? Yay or nay? Okay.
Yes, because e to the negative x.
Okay. And then that implies that c is equal to negative 1. So your answer here is y is equal to 1 minus e to the minus x. Okay. Now, frankly, seems like we're done, okay? Because that's when x equals 0, and that's the only part you're dealing with, so that would be it. But they want us to go on, I think, and do it for the other part as well, okay? I wish I had more room. I'm going to erase a bunch. Is that okay? Because I don't think we need this anymore. Oh, why did I erase that? I'm being dumb here. Okay. Oh, I better erase it all. I'm not thinking ahead well enough at the point. Okay. I do want to hang on to that.
So now we're doing it where f of x equals 0.
Yeah. Okay, so you get dy dx, that's why did I erase it? You know, I don't know, is equal to 0. Now,
We know it's e to the x.
the rest of this doesn't matter, I don't think, because this is where x is greater than 1, so why put in the initial condition here? Because that's where x is equal to 0. But let's see what they do. I don't think... all right, let's just see what we got. Everything else was the same. The p of x was equal to 1. Your integral of that is equal to x. Your integrating factor is e to the x. And you multiply that and you get e to the x dy dx plus y e to the x is equal to 0. And this you hope to be a perfect derivative of e to the x times y. Okay, and sure enough, derivative of e to the x is e to the x times y, that's that term. And derivative of y is dy dx times e to the x, that's that term. It is. So then do your dx over here, and that's going to be d of e to the xy is equal to 0 dx. Okay? And when you integrate both sides of that, this becomes e to the xy is equal to what? A constant. Probably a different constant from before, but whatever. So now y is equal to c e to the minus x. And that's what we got for the other part. Okay? Now, what we would like is for this is a function of x, this is a function of x. We would like for them to be the same thing at x equal 1. Wouldn't that be nice? Because that's your discontinuity here at x equal 1. So let's see what happens when x equal 1. Here y of 1 is equal to, and this we got our constant already solved for because that was when this was in the domain. Here we don't because that's not in the domain. So y of 1 here would be what? Pretty easy. 1, good, minus e to the negative 1. Okay? And down here, y of 1 would be c e to the minus 1. Right? And if you want those to be equal, you could then multiply everything on both sides by e. That would work, wouldn't it? And you'd have c is equal to e. Now you're multiplying by e. See, if you multiply this by e, this by e, and this by e, right, be e. I've already messed myself up here. E minus 1 is equal to c. Right? Because e to the minus 1 times e is 1. E over e. Right? That is e over e. Whether I have it on both sides, I'm not sure, but I do. C is equal to that. So down here, and this is this c, not the c we did before. So down here, you would have y of x is equal to e minus 1 times e to the minus x. Okay? That's a little awkward in a sense, because you can multiply it through by that. You'd have e to the 1 times e to the minus x minus e to the minus x. Well, this is the same as E. Wait a minute. Wait, that's an X there. I said X and wrote 1. Okay, when I distribute here, you got E times E to the 1 times E to the minus X. Then distribute that, you get minus E to the minus X. So this would be E to the 1 minus X is equal, or minus E to the X. Is that right? I've got myself lost here. Yeah. All right. So the y of x down here, you can write it either way. Which way did they wind up writing it? They do E, they did it like I left it at the bottom. E minus 1 times E to the minus x. Okay. So I need to write my answer that way. So let me erase something. I can erase all this now. All right, I think I can. All right. So our solution is y of x is equal to, because this is an initial value problem, equal to one minus e to the minus x anytime 0 is less than or equal to x is less than or equal to 1, and it's equal to e minus 1 e to the minus x anytime x is greater than 1. So there's a solution. And it's continuous. Not continuously differentiable, because there's a node, I don't know what to call it, a peak, almost a cusp there at x equal 1. But it is continuous throughout. Okay. Make sense? All right, how are we doing on time? We go till 3:45, or a little short of that because we did get started a couple minutes early. All right, now, all right to erase, or is that you need a little longer? Okay. In mathematics, science, and engineering, some important functions are defined in terms of non-elementary integrals. We've hit a few of these before. Here we go again. Two such special functions are the error function and the complementary error function. And here's how we define each of those. The error function is ERF of x. Error function of x is equal to 2 over root pi, one of my favorite numbers of all time, times the integral from 0 to x of e to the minus t squared dt. Okay? And the complementary error function, which is ERFC of x, even though as they say complementary error function, they write it as error function complement of x, is equal to the same 2 over root pi times the integral from x to infinity of e to the minus t squared dt. Okay. Now, what's that? Oh, okay. Now, they say here, from the known result that the integral from 0 to infinity of, excuse me, e to the minus t squared dt is equal to square root of pi over 2. And they say that result is proved in Appendix A. I can't wait to get there and see it, okay? We can write that 2 over root pi, which is common to both integrals, of the integral from 0 to pi would then be e to the minus t squared dt would then be 1. This is all sorts of blah, blah, blah. But they say they know this. This is supposed to be common knowledge. ERF of x. Huh?
Of course.
Of course.
Have we seen this as a normal distribution curve?
Yes, that's exactly what it is. You beat me to it. Okay?
So that's what it is.
I'm sorry.
You should be obvious.
What's that?
I said it seems obvious because we've seen the functions maybe someplace else.
Right. That the integral from 0 to infinity of e to the minus t squared dt is equal to square root of pi over 2. Okay? So that is something that we're supposed to know already. Yeah, right. And we can then write that if you multiply both sides of the equation by 2 over root pi, this is equal to 1. So that's how they get the second part. Okay? Which, if you think about it, what that says, sitting too long, this thing from 0 to x, this thing here, plus this thing, which is from x to infinity, add those two together, you should get 1. That's what they mean by being complements. This is part of that, that's the other part. So whatever error function is, 1 minus that is your complementary error function. Whatever the complementary error function is, 1 minus that is the error function. That comes from this. Okay? Now, thinking, as Bill just said, if you're talking about a probability distribution curve, that kind of stuff, if the probability, let's say your error function is something like that, okay, and from 0 to x gets you this far, you're just in this part, then the rest of it's going to be there. The total area under that curve is 1, and that's what this is saying. So if you know what part is, the other part is 1 minus the complementary part. Okay. So that's what leads to error function of x plus the complementary error function of x is always equal to 1. Okay. Now, because of its importance in probability, statistics, applied partial differential equations, the error function has been extensively tabulated and know that the error function of 0 is 0, is what obvious function value. Numerical values for that can also be found using computer algebra systems such as Mathematica. And did you say you were familiar with another one? Okay, maybe it was another class. Somebody else. Okay. If we're solving an initial value problem, number 6, go back to that, way back to row 6, page bottom of page 57, something like that. If we're solving an initial value and recognize that indefinite integration of the right-hand side of 5 would lead to a non-elementary integral, then we saw in example 5 of 2.2, it is convenient to use instead definite integration over an interval x of 0 to x. In other words, blah, blah, blah. Okay. Let's do example 7 if we can. That paragraph there seemed to be running us in circles. It's all true, I'm sure, but a big part of saying what difference does all that make?
That's what I was thinking. I thought we were going to solve something.
Yeah. So dy dx minus 2xy is equal to 2 with the initial condition y of 0 is equal to 1. Okay. If that 2 on the right-hand side had been a 0, you could solve this separable. With it not being a 0, you can't. Okay? So can't do it by separation of variables. So what's your next best?
You make it p of x.
Ah, yes, this is linear. Because dy dx is only raised to the first power, y is only raised to the first power. No cross terms, no denominators, nothing else with y's in them, or dy's in them. So yeah, so your p of x, what were you saying?
-2x.
Is equal to negative 2x. And what do we do with that? Integrate minus 2x dx, and what do you get?
Negative x squared. Yeah.
You don't need the dx anymore. Just negative x squared. Right? Okay, and what do you do with that? You eat it, right? Okay. That's a new term. You won't find that in any other math book anywhere. Okay, you eat it. Okay. And that's what you multiply by both sides. So it's e to the minus x squared dy dx minus 2xy e to the minus x squared is equal to 2 e to the minus x squared. Okay? Now supposedly this is a perfect derivative of something. What would that something be? Okay, hopefully it's y times e to the minus x squared. All right, goodness gracious. Is it? The derivative of this, you get derivative of the first, dy dx, times the second. Yep, that works. Plus the second, or the first, times the root of the second, which is e to the minus 2x squared. That's good. Times a minus 2x, and that's good. So yeah, that is. All right. That's equal to 2e to the minus x squared. All right. Take our dx's and move it to the other side. Now that's a perfect derivative. And when you integrate both sides in, you get y e to the minus x squared is equal to 2, okay, integral, yeah, but you can't do anything with that, so you could write it all out like that. Oh, let's do it, won't hurt anything. E to the minus x squared dx, okay. Then you can multiply both sides by e to the x squared, so you get y is equal to 2 e to the x squared, yeah, times the integral e to the minus x squared dx. Okay. Plus c. Okay. I think I've done it right. I'm losing focus fast here, folks. This is, my writing's getting awful. Okay. Now, if I wish I still had the previous slide up, but I can't have but one slide up at a time. If you had multiplied and divided this by root pi, okay, now one thing I noticed they did here, they didn't multiply through by e to the x squared. I guess they didn't want to. So let me go up and erase that. I was saying it does sort of muck up the issue here. All right. We're running out of time. You have y e to the minus x squared equals to, now, if we had the previous there, we would have seen that 2 over root pi. So we want to over root pi, so we have to multiply by root pi. And then you have here a 2 over root pi. Times the integral. And now we're going to from up here, they kind of magically say your x of 0 no, it's not from there.
They like to find the interval.
Yeah. This little statement they have here really leads, yeah. Because the indefinite integral on both sides of equation 13, which is what we have right here, this is their equation 13. Well, before we integrate it, it's their 13. Down here. before you do the integral. So let me wipe the integral. Yuck! I erased everything. Is that a sign? Goodness gracious. Hit the wrong button and then went to hit the other one. My pen hit the board and it erased it all. Huh? Let's go back to 13. That's what I was going to do. D by dx, this is backing up a lot here, e to the minus x squared y is equal to 2 e to the minus x squared. Okay, that's what we had. And it says because the indefinite integration on both sides of that leads to the non-elementary integral, and that's what I had done. Do this out, do a dx here, and then integrate this and integrate that, and you get to the e to the minus x squared y is equal to 2 times this non-elementary integral. It says we identify x0 as 0. And where in the world, oh, I see. Okay. They're calling this value for x, x sub 0. Okay. Now why that? Because in the form that we had, that was what was always the lower limit of the integration. So that's where that comes from. Okay? And use definite integration over the interval 0 to x, and that would produce the integral from 0 to x, and since you put the x up here, you have e to the minus t squared dt, or any other variable you wanted to. T is just as good as just a dummy. We used before, whatever. Okay. All right. Now, they also did something else. They do this also from 0 to x, changing that variable, 0 to x here. Well, when you put an x in there, they go back and change this to a t and make it a dt here, all that kind of stuff. But when you do this, you get e to the minus x squared y, okay? And then when you plug in for t 0, you just get, when y is equal to, when x is 0, your y is, I'm sorry, I wrote that down wrong, is equal to 1, okay? That was your original problem. Y of 0 is 1. You named that 0 to be your x of 0. And I'm running out of time now. So you get this part when you plug in the x up here, right here, that x, you get this. And then when you plug in the 0, when x equals 0, y of 0 is 1. So you get minus e it just minus 1, okay, because that just becomes a minus 1, okay, and that's equal to, well, this part over here is going to be a 2. If you multiply by pi and divide by pi, then you get your error function. This is 0 to x e to the minus t squared dt. So what you have here is e to the minus x squared y minus 1 is equal to pi times the error function of x. Okay? And if you want to solve for y, add 1 to both sides. So you have e to the minus x squared y is equal to pi ERF of x plus 1, and then multiply both sides by e to the x squared. Okay, so this will be pi e to the x squared times the error function of x plus e to the x squared, because you're multiplying that by 1 as well. Okay. Phew. Oh, wait. Yeah. Okay. All right, there's it at the bottom. I couldn't find it. Y is equal to e to the x squared. You can factor that out. 1 plus square root of pi times the error function. Yeah. They rewrote it like this. E to the x squared times 1 plus pi ERF of x. Okay. Yeah. I lost where they're going. Okay, they have a little blurb, lost use of computers at the bottom. Hey, we've just finished the section. Almost. Homework exercises, any of the odds 1 through 24, 1 through 23 that are in the back of the book. Any of the odds 25 to 35 that are in the back of the book. Any of the odds 37 to either 37 or 39 if they're in the back. 41 if it's in the back. 43 if it's in the back. 45 if it's in the back. And this sine integral function, it drives me nuts that they put something new in the problem set. If that was important enough, put it in the section, but they put it here. And then they have the Fresnel sine integral function. And frankly, you can do whatever you want to with those two. Fresnel may be a good paper topic, or sine integral function. Who came up with this thing? What is it used for? What difference does it make? They define it here, but they don't tell you anything else. Usually the discussion problems are not in the back of the book. If you find any that are, you can try to do those as well. Mathematical models, you can look at that if you want to. Computer lab assignments, if you have any type of computer algebra sets. Computer algebra, oh, what does that S stand for? System. And if you have one, use it, but if not. All right, before we leave here, I will want to say a little bit about some of the bold words in the remarks. I don't like to fiddle with the remarks too much. They can bog you down like crazy, but there are a couple of important words there that we may or may not run into in the future, but you'll probably run into them sometime. And in fact, the sine integral function, Fresnel sine integral function are there. So I won't say much more about them. Just a little bit on, especially that Roman numeral 2. The driving function, input, output, or response, that kind of stuff. All right, good deal. Any questions? Sorry I ran a bit longer than I intended. I got to book it over to the Birmingham campus. But I appreciate your attendance, attention, and all that kind of stuff. Let me close this out. And I just closed the book. I didn't mean to.